Hey class, Mr. Mojan here with a video on looking at linear programming and solving a real-world cost problem. So this problem says we have two brands of fertilizer available to purchase, GrowFast and Quickies. GrowFast bags contain 2 kilograms of nitrogen and 4 kilograms of phosphate, while Quickies bags have 4 kilograms of nitrogen and 3 kilograms of phosphates. A bag of GrowFast costs $60 a bag, while Quickies sells for $30 a bag. The field to be fertilized requires at least 16 kilograms of nitrogen and 24 kilograms of phosphate. How many of each brand should be bought to minimize the cost? And what is that minimum cost? So a lot of information to digest there. If you recall, one of our first steps in identifying a linear programming problem is to identify the objective function. So what is it we're actually trying to maximize or minimize, or in general optimize? So minimize the cost kind of gives that away. Our goal, our objective function here, is going to be to minimize some sort of cost. So C is going to equal something. Well, let's go ahead and define our variables. Our cost is dependent upon how many bags we buy, right? So let's call X, it happens to come first, so let's call that our bags of GrowFast. I guess Miracle Grow was copyrighted. And Y, let's call that our bags of Quickies. So Y is our Quickies bags. Fun name. So if X is GrowFast and Y is Quickies, then now we have a way to figure out our cost, right? Let me use the highlighter here. Bag of GrowFast costs $60 and Quickies cost $30. So in terms of X and Y, every GrowFast bag would be 60 times the number thereof, X, and every Quickies bag would be 30 times the number thereof, or Y. So our goal is to minimize this thing right here. So let me give myself some room here now that we have those. Let me just shrink this text. There we go. Alright, so this is the hard part, is to figure out our restrictions. Let's take a look here. Our field needs 16 kilograms of nitrogen at least. So more than that's fine, but we got to have at least 16 kilograms of nitrogen, and we got to have 24 kilograms of phosphate. So you might think that 16 and 24 might be your variables somewhere, but keep in mind we already have our variables defined. Those are X and Y, number of bags of each kind. So really our restrictions actually boil down to how many units of nitrogen and phosphate each bag has. So we basically want to make sure that we get enough nitrogen and enough phosphate into our field. So let me write out first here the nitrogen restriction, or constraint to use a more appropriate term. The nitrogen constraint. We have to have at least, so another way of saying at least is our quantity must be greater than or equal to 16 units of nitrogen, or 16 kilograms, which I'm getting from right there. So every GrowFast bag has 2 kilograms of nitrogen, right? So for every GrowFast bag X, I'm getting 2 nitrogens from that, or 2 kilograms of nitrogen. Meanwhile, from every Quickies bag, which is Y, I'm getting 4 kilograms of nitrogen. So it's 2X plus 4Y. So for example, if I bought 1 bag of each, I'm getting 6, right? 2 plus 4 kilograms of nitrogen. Obviously not enough, but it would scale up in this way, where every Quickies bag gives me 2, and every GrowFast bag gives me 2, and every Quickies bag gives me 4. So there's one of my restrictions, right? Looking at the numbers in the problem, recognizing that I have to have enough nitrogen. So keep in mind, this is actually a minimization problem. Some of the problems we've seen in class are maximization problems, where you have a cap, right? A number of hours or amount of money. Here, we basically have a minimum restriction. We need at least 16 units. More would be great, but you want to get as cheap a cost as we can while still meeting our restriction. So our other restriction besides nitrogen is to make sure our field has enough phosphate, another mineral. So let me express the phosphate restriction or constraint. So let's take a look. We need at least 24 kilograms of phosphate, right? So at least 24 kilograms of phosphate. So whatever I have over here, that amount needs to be greater than or equal to. Greater than is great, but equal to is fine. 24. Let's see, I have, for every bag of X, which is grow fast, I'm getting 4 kilograms of phosphate, so pretty good. And for every bag of quickies, which is Y, I'm getting 3 kilograms of phosphate. So there we have that expression for our phosphate restriction. Since X and Y represent physical quantities, don't forget we usually have the non-negativity constraint, which is to say you can't have negative bags of either of these, even though that would make your cost very low. So X is greater than 0 and Y is greater than 0. So as I mentioned, this was the hard part of this problem, I would say. The hardest is to figure out from the text to extract all this information from there. So just to review briefly, what is it we're minimizing or maximizing? That's this cost. Let's define X and Y, and that will make this make sense in terms of money. Because X grow fast bags cost $60 and Y quickies bag cost $30 respectively. Then you want to figure out, well, what's your limit, or what's your minimum requirement, depending on if it's max or min. And we need at least this quantity of nitrogen and at least this quantity of phosphate. So that clues us into what our bounds should be in terms of our restrictions. And then it's just a matter of expressing the amount of those restricted quantities or constraint quantities in terms of variables, which we did in purple and blue, as you can see here. So I have the equations already listed out here. If you recall, one of our steps here is to graph our system, to actually visualize our feasible region. So a quick way to do that is to use the intercept method. So if I cover up this value here, I have an x-intercept of 8, so that would be 8, 0. And if I cover up the x value, I have a y-intercept of 4, so 0, 4. So I'll graph these in just a minute. I'm just listing out the intercepts. Over here, if I cover up the y value, I have an x-intercept of 6, so that would be 6, 0 for my second constraint. And if I cover up the x value, I have a y-intercept of 8, so 0, 8. This limits me to the first quadrant, so this gives me a sense as to what my graph might look like. Because you don't want to put your units on the axes necessarily right away, because you don't know how big or small your numbers are until you have enough to compare against. So our first line connects these two, and our second line connects those two. So I have those on the next slide here. Time to actually make a graph. So I went ahead and colored these. Let's see, our biggest x value appears to be 8, right? 8 is bigger than 6. So I'm going to go out to 8. I'm going to guesstimate, I don't know, 8's probably around here somewhere. And if that's the case, then this is about 4, so keep that in mind. So there's my 8. And while I'm at it, let me go ahead and mark the 6, because that's my other x value, right? So it's going to be, if this is 4 here in the middle halfway, then 6 would be roughly around here. So that's going to be my 6. For my y value, I want to have a fair axis here, so I'll sort of visualize this little square, which is going to represent 8 in both directions. So this will also be 8, which incidentally is my y-intercept for one of my other variables, which is the other bag company. And likewise, 4 is going to be my y-intercept for the other quantity, and it's going to be about halfway. So if I connect these with lines, I would have these two right here. These two right there. Now in terms of shading, so they're solid lines because we were dealing with greater than or equal to scenarios. If you recall, the little trick I showed you was that when you're dealing with less than or equal to scenarios, which we typically see in maximization problems, here we have minimization. Greater than or equal to, essentially you're going to shade away from the origin. So everything on the far side of the green line and on the far side of the blue line would basically be all of this region here, and this will test my ability to stay within lines, which is not necessarily the easiest thing. And keep in mind, so all this space here, is this a bounded or unbounded region? As you can see, this is an unbounded region, because there's no limit to how much gray I could put in theory if I zoomed out. So right away, our feasible region starts to look like this. And then, of course, it's sort of unbounded here, so I like to put little squigglies to indicate we're just ripping out part of it. So our corners would be right here. Do these in purple. There, there, and there. Well, two of our corners are pretty straightforward. This is going to be 8, 0. This is going to be 0, 8. The only other one of interest, which looks like it might be pretty curious here, is that one there, where the two lines cross. So we have two of our three corner points. If you recall, the fundamental theorem of linear programming says essentially your optimal value will be at a corner point of the feasible region. So we need to find what this is because that might be smaller than the other two. So to find that value, we're going to focus on these two restrictions here, right? So I have them here. We're basically going to treat them as equations because we're more concerned about the lines than the regions at this point. So 2x plus 4y effectively equals 16. This is kind of a safe assumption. And 4x plus 3y is going to roughly equal 24. So this is a good candidate for the elimination method. The reason is this is a multiple of this right here, 2 and 4. So if I double the first equation, I'm going to make everything twice as big. But I need to make them opposite, so I'm going to multiply everything actually by -2. So my first equation becomes -4x minus 8y equals -32. My second equation remains untouched, so this is called the elimination method if you recall. So that's 4x plus 3y equals 24. I now have these pair of opposites as desired, so these will cancel, giving me -5y equals -8. Negative by negative cancels, and I get a positive 8/5, which is about 1.6. Now this is a curious result. Y represents, if you recall, the number of Quickies bags. Well, going to the Home Depot or some other store and asking for 1.6 bags or something is sort of an odd request. So this is a clue that maybe this result is not necessarily the best one. But let's soldier on and see what happens. We need to find the number of Quickies bags, Grow Fast X bags that this would correspond to. So I'm going to plug that into my original function here. So that's going to be 2x plus 4 times 1.6 is going to equal 16. So do a little bit of math ahead of time. If I multiply these together, I get 6.4, I believe. And if I subtract from both sides, I'll get 9.6. And then divide, and I get 4.8. So 4.8 of one bag and 1.6 of the other would represent a corner point of the region. So now we have all three of our corner points. We have, let me do this in purple again. We have 0, 8, 8, 0, so all of one bag in either type, or a combination of both bags for our feasible region. So now all we got to do is to plug in these 3 points into our objective function and figure out the biggest or smallest value. So we have 0, 8. So if I plug that in right here, choose a different color. That'd be 60 times 0 plus 30 times 8. Would give me $240. 80 would be 60 times 8 plus 30 times 0. That cancels like that one did. And you would get 480. These numbers aren't quite as pleasant. 60 times 4.8 bags, presuming that the store will allow us to buy such a weird quantity. 30 times 1.6 bags, and you get $336, I believe. Something in that ballpark. So right away you can tell that the smallest of these numbers would be this guy right here. So you should buy, let's see, looking at this quantity, 0 bags of X, which we call to be Grow Fast in our context here, 8 bags of Quickies, cute name. How much will that cost? A mere $240. That'll give us just enough fertilizer for our field, so that's going to be the minimum value. Hope this helps.